Number 7 of our fall 2011 exam. 1200 kilogram car, top of a hill, elevation and a speed. Halfway down the hill, we're applying a force. Bottom of the hill, at a given elevation, we stop it with a spring. What's the energy loss on the way? Conservation of energy problem. We need to define our two states. So let's draw a picture and label everything. So blah da 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 da. Okay, so up here we at state 1. Okay, we got a 1200 kilogram car. Elevation 54 meters. And speed of 12 meters per second. Okay, halfway down the hill, a 600 Newton force is applied in the direction of the coaster. It's moving for a distance of 75 meters. Okay, so what we're saying here is for 75, I thought I changed colors here. For 75 meters, as this thing's moving forward, we're applying a force of 600 newtons. So that's some sort of engine or something kicking in and making it go faster. Okay. At the bottom of the hill, elevation 16 meters. Alright, so now we're down here. Okay, what it calls the bottom, but we're still 16 meters off some reference point. The car is brought to rest by compressing a spring with a K of that value. So we've got some sort of spring here that's going to stop it. Okay, K is 7,800 newtons per meter, and the delta X is going to be 8 meters. Okay, so a lot of information in here. The state that we're looking at, state 2 here, is where it's already stopped. So the spring is compressed, the velocity is 0. We're at this elevation. Okay, we have energy coming in, and we also have some sort of E loss here happening during the run. Alright, so this one truly does use most of the terms of the energy equation, so we'll write it out here. K1 plus UG1 plus UE1 plus work in is equal to K2 plus UG2 plus UE2 plus E loss. Okay, so if we use our datum and where we're given here, neither one of our gravitationals are 0. That means our final kinetic energy is 0. We're going to solve for energy loss. We'll have a bunch of spring energy at the end. Okay, we are going to factor in our work in. The spring's initially uncompressed, so that term will be 0. Okay, so a lot of terms to factor in. Let's start writing it out. So I'll write it out generically first. 1/2 mv1 squared plus mgh1. The work in is going to be force times the distance. Okay, and that's going to be mgh2 plus 1/2 k delta x squared plus E loss. Alright, so plugging in numbers. 1/2 mass 1200 kilograms. Velocity 12 meters per second, and that's going to be squared. 1200 kilograms times 9.81. Okay, looking ahead a little bit, I have an H1 here and an H2 here, both multiplied by mg. Alright, so I'm just going to write that as H1 minus H2, the difference in the height, so 54 meters minus 16 meters. Okay, plus force times the distance, so that's my 600 newtons times 75 meters. There's my work in. And let's see. I'll go ahead and move this term to the other side, so I'm basically solving for energy loss. Okay, so I'm going to subtract off this value right here. So my energy, 1/2 kx squared. Okay, so minus 1/2, 7,800 newtons per meter times 8 meters squared. Alright, so this whole term is my energy loss. So bring in the calculator. Let's type everything in. 0.5 times 1200 times 12 squared plus 1200 times 9.81 times 54 minus 16 plus 600 times 75 minus 0.5 times 7,800 times 8 times 8. 329,000. So E loss is 329,000. Okay, let's look at units for a second. We'll start over here on the right. We have newtons over meters times meters squared. So that's a newton meter, which is a joule. This term has newton meters. This term has kilogram meter per second squared. That's a newton times a meter. And this is kilograms meter squared over second squared, which is also a newton. Newton meter or joule. So 329,000 joules lost.